Okay, so let's look at question 5. Gabrielle is planning for retirement, and she estimates that she'll want to be able to withdraw $2,000 each month for 17 years once she retires. She opens a Roth IRA and finds investments that she expects to return 4.85% interest compounded monthly. So our first question is, how much will she need to have in the account when she retires in order to meet her goal? So let's notice that she wants to be able to withdraw $2,000 every month for 17 years, and her interest rate is 4.85%. Now, when we think about withdrawing or pulling something out of an account, we want to think about the same formula we used for loans because we're pulling something out of an account. So we're going to use this one that has the negative exponents. And think of, if you're withdrawing something, if you're taking money out, if you're making a payment, it's going to be negative. Or if you're withdrawing, even if it's for yourself, it's going to be the negative exponent. If, on the other hand, you're saving things up, it's going to be the positive exponent. So we're going to use this top one first. We'll see, though, that we may end up using both of them. All right, so let's fill in. We know the amount that she is going to want to withdraw is $2,000. So we're going to put that in for D. The interest rate, I believe, was 4.85%, but let's look back. 4.85%. So let's change that into a decimal. 0.0485. And that's going to go over monthly payments, so 12 times a year. And that is raised to the negative 12 times, I believe it was 17 years, but again, let's check. 17 years. Okay, so 17 years. And this is going to go over 0.0485 over 12. All right, now let's work through this thing. I'm going to do inside the parentheses first. So 1 plus 0.0485 over 12. And that gives me 1.004 041667. And we don't want to shortcut these. We need to write our decimals out. And then negative 12 times 17, I'll go ahead and do that exponent. It's 204. It's negative 204. Now, when we actually raise this to this exponent, we want to be sure to put that in parentheses as we raise it to that exponent here in a minute in our calculator, because otherwise we will get an error. All right. And then this part on the bottom is actually the same as this without the 1. So 0.004041667. All right, let's continue from there. Now let's take the 1.004041667 and raise it to the negative 204 power. 0.004041667 to the... All right, and we are going to get 2001 minus 0.439 18332 1. All right, over this. All right, and now let's just continue. Let's do that subtraction on top. So I will do the 1 minus the 0.43999 or 0.439183321, and that's 0.560816. 679. And now I'm at the point after this that I can put everything into the calculator at once, and I shouldn't run into any glitches. So we can go ahead and enter 2,000 times the 0.5608166679 divided by this bottom, and we should get what the future value that we need to have is going to be. And that amount is quite huge, and $2,000 is really quite a bit for retirement payment, so it's not really that surprising. 2,775,000. Oh, I'm sorry, it's not 2 million, it's 277,517. Otherwise, 2 million would be quite a bit. And 51 cents. All right, and let's go back. That's part A. And of course, as the teacher, of course, I've got the power to go, yes, that's what we've got. All right, now, how much will she have to deposit each month for the next 40 years in order to get this balance at retirement? All right, now this time, she's saving. She's putting away a deposit in her own account in order to save up for retirement. So we're going to use the second formula from the sheet a while ago. And let's keep in mind, though, that our years now are 40 years. All right, so let's go back then, and let's again assume that we're still using 4.85% interest, and we know what she needs to have as her future value from question A already. So we're going 40 years, monthly, 4.85%, and we're going to use our second formula. Okay, so the future value that she needs, now I said the second formula, I mean this one right here. She is making deposits into a bank account, saving money up. So we're going to use the savings annuity formula right here. The future value we want is this right here. So the left-hand side of the equation is $277,000. And the right-hand side, we don't know how much she's going to deposit per month, so that's our unknown. But we're going to have, for the savings, 1 plus, interest rate was 0.0485. Again, monthly. And she's going to do this for 40 years. So 40 years times the 12. Right here. Going to save for 40 years. And then the bottom has really part of the top in it. So we have just filled into the savings annuity formula. This one here. All right, now, just like we did with the prior one, let's work this out. Now we can cheat just a tad here, and I'll show you what I mean. I'm going to leave this the same. All right, but 1 plus 0.0485 over 12, we've already done that computation up here. it was this decimal right here. So I'm just going to rewrite that decimal so I don't have to put them in my calculator again. 1.00404. Um, 1667. Now, unfortunately, I can't duplicate the next part because our exponent is going to be different. 40 times 12 is going to be 480 for an exponent. The bottom, however, recall this is always just this part without the 1. So 0.004041667. Okay, now let's go ahead and do this number here raised to the 480th power in our calculator. It's going to end up giving me 6.931 597 278. And then I'll still have my -1 and the bottom. And let me see if I can move this just a little bit, and then the page, it's hard to get it to go to a second page in Word, so I might have to fool with it here in a second. All right, so next we want to take the 6.931597278 and subtract the 1 on top. So we'll do that. So I get 5.931597278. And then our last step, our second to last step, let's divide this stuff out with that is with our D. And that is going to end up giving us 1467 .611577. All right, now I've got an equation and I've got something being multiplied by D. So to get rid of this item that's being multiplied by D, let's divide it out on both sides. So I will divide it out. Let's see what we get. At this point, I'll go ahead and round it off to a dollar amount. So $189.09. Doesn't seem like much, but let's remember that she is saving for 40 years. And of course we can check here, and it is correct. Now, how much interest will her deposits earn between now and retirement? Okay, so to figure that out, let's go back. Let's remember she is paying $189.09 for every month of the year for 40 years. Let's multiply that out, and that's the amount she would have put into the account. So she put $90,763.20 into the account. To figure out how much interest there is, let's take that future value amount, that's how much would eventually be in the account, subtract off the $90,000 that she paid into the account, and that will be the amount of interest she has earned. And that is $186,754.31.